be lecturing on, Hida Theory, which is basically a description of the space of Lambda-adic forms and some of their properties. Okay, so let me recall quickly the definition of a Lambda-adic form. I keep writing yesterday and tomorrow, but of course I mean yesterday was Tuesday. It's actually Wednesday really, but I meant Tuesday. What we did was we defined the Lambda-adic form as an infinite series belonging to a power series ring I. So I is actually a finite extension of the power series ring, ZP power series X. So it's a formal Q expansion like this with coefficients in I. If for all arithmetic specializations, which means all homomorphisms from I to QP bar, which lie over very special kinds of homomorphisms, namely the ones lying over the usual homomorphisms from Miyazawa theory. X goes to zeta, 1 plus p to the k minus 1. Right, so zeta is a p power root of unity. It's actually a p to the r minus 1th root of unity, where r is bigger than or equal to 1. So it could be trivial, for instance, and then k is integer bigger than or equal to 2. So in the definition of Lambda-adic form, we only look at k greater than or equal to 2. So this Q expansion, when you specialize under such homomorphisms, you get nu of f is the, so nu of f, of course, is you just, okay, maybe I'll write it again. N equals 0 to infinity. You apply nu to all the Fourier coefficients. So you actually get something in QP bar, power series Q, is the Q expansion of a classical cus form or modular form of level NPR. Today I'll basically be looking at cus forms, but for now let us just recall the general definition for all modular forms. Weight k greater than or equal to 2. Maybe I should have written the weight first. Level NPR and character chi, which is psi omega minus k chi zeta. So that is the definition of a Lambda-adic form. Under all these specializations, you just get these classical forms. Can everyone hear me? I'll just pause for a second. Is it okay?
Yeah, sure.
Okay, so today we want to study the space of Lambda-adic forms, and actually we want to impose a p ordinary condition, because all the examples that I gave, you notice they were p ordinary, and the theory is much better. In fact, the theory was invented only for p ordinary Lambda-adic forms. So I'll define what it means for a Lambda-adic form to be p ordinary. But for now, let m n lambda. So I should have said that p is of course a prime and n is co-prime to p. Right, fixed and odd prime, and right, I didn't write all this notation down. Omega is the mod p cyclotomic character, psi is a character of conductor np, chi zeta was a character of wild character of conductor p to the r. So let Mn lambda be the I module. So more formally, this should be called an I-adic form because it's taking values in I, but I'm just speaking loosely here and calling it a lambda-adic form. And of course, when I is equal to lambda, it's the same thing. But technically, these are I-adic forms. And you can add them, multiply by scalars in I, and you get an I module. So it's an I module of I-adic forms, but let me write lambda-adic forms. And let Sn lambda. Notice this is very much like the notation for usual modular forms, right? Except I don't have a weight. So lambda-adic forms don't have weights because they see all weights at the same time. Specializing under different weights, you get a different weight modular form. But they do have a level, and it's only the tame level n. Where's the p hiding in this notation? The p is hiding in lambda. So the level is really np to the r when you specialize. But the n is hiding here, and the p is hiding here. Well, the n is not hiding, it's explicit. Lambda p is a little inexplicit, but it's in the ZP bar series X. This is the I module of lambda-adic cusp forms. Okay, so here I have not fixed the Nabin typist character psi. It can be any Nabin typist. So let's decompose. So note that these spaces have a decomposition according to the character psi. So actually C star, but maybe I'll write Q bar star because they actually take values and add big numbers. And that's sitting in QP bar, etc., ZP bar. So psi, and this will lead me to something which I have been a little bit sweeping under the carpet. Where are various things valued? Sometimes modular forms are in QP bar, sometimes they're in complex numbers, etc. But we'll address that issue in a second. And similarly, you have a decomposition of the space of lambda-adic cusp forms into the lambda-adic cusp forms with Nabin typist character psi. It's not really the Nabin typist, that's the character of the form. The actual specializations have psi times omega minus a times chi zeta. So, but you can decompose this according to all characters, Dirichlet characters of conductor Z, of conductor NP, okay, according to the tame conductor. Okay, so these are the lambda-adic forms up here, the ones with character psi. So this is a lambda-adic form with character psi from Z mod NP star to C star or Q bar star. Okay, so this is just notation. This was the definition of the space of lambda-adic forms, right? And this was the I module of lambda-adic forms, and we decompose this according to various characters. So now let's come to some definitions where people were asking about yesterday as in on Tuesday. Say a lambda-adic form is normalized if, well, whenever you define a property for a lambda-adic form, the way you do it is you say that all arithmetic specializations of weight k greater than or equal to 2, all these particular cusp forms have that property. If that's true, then you say the lambda-adic form has that property. So it's normalized if the first Fourier coefficient, as in A1, the Q coefficient, this is a bit different from Professor Ramke's talks where he's defining the normalization for the A0th coefficient being 1. This is the first Fourier coefficient as in A1 being 1. And if all the specializations have A1 equals 1, then it's fairly clear that the lambda-adic form also has to have the power series A1, which is an abstract power series. It should be 1. So you can think about that for a second. So normalized, let me, instead of saying all specializations have A1 equals 1, let me just straight away say that the lambda-adic form has first Fourier coefficient 1, the Q coefficient. Is an eigenform? Well, you can guess what that is. If nu of f is an eigenform, can you see? Maybe I lift this up a bit. Nu of f is an eigenform for all Hecke operators. So this is for all, right? Nu lying over k zeta for all Hecke operators Tn. Okay. Now notice that n and p are in the level. So n is definitely in the level, but p is also in the level. So I want to emphasize here, very important, in particular, the operator Tp, the p Hecke operator is not called Tp, it's called Up, because p is in the level. In particular, an eigenvector of the Up operator. Okay, Tp is called Up, it's just a different name, but it's a bit, there's a reason why it's called Up. And the reason is that the Hecke operator Tn has p plus 1, a summation over p plus 1 things, but the U in general, but when you divide the level, like p divides the level, then it's a sum over p things. So in the formula, so you leave out one of the coset representatives. Okay, so more precisely, it is for the Up operator. Can I flip the page?
Yeah, you can fill.
Okay, great. Okay, so we've defined what it means to be normalized. We defined an eigenform. By the way, there's a Hecke theory. I swept that under the carpet. And it's identical to the usual Hecke operators acting on classical spaces of cusp forms and model forms. Exactly the same formulas. So there's no point repeating it here. We say it's a new form. Well, this is a bit subtle because P is in the level. So, but let us just say it's a new form. If all the specializations lying over these forms is a new form, if all these forms are n new. Okay, so new at n. So it might be old at p. And usually the specializations are old at, it's often they're old at p, but what they are is they're p stabilized n new forms. In other words, they're either new at p, or if they're old at p, they're coming from the p stabilization of a pure n, purely n new form, classical n new form. We saw how we did p stabilization last time. There's a way to go from a form of level n to a form of level np by taking a difference of two old forms. And that process of p stabilization are the actual modular forms that you get when you have a form of level np. So it's an old form, but only a difference of two old forms in a very specific way. And sometimes if, you know, the second term and the difference is not there, then it's just genuinely, it's just p new already. Anyway, so this is the only condition that we put, that it's n new, and I'm not putting any condition at p, but that's what I just described is what will happen. And finally, primitive, if all of the above. So this is exactly the same definition I made for classical cusp forms. Okay, so these are the space of Lambda-adic forms and also some special kinds of Lambda-adic forms. So here, now, if you look at the space of classical modular forms or classical cusp forms and things, you notice immediately that the space of primitive forms, the set of primitive forms is actually finite, right? This is the usual thing that if you have a basis of eigenvectors of the Hecke operators, or at least outside a finite set of primes. So, but unfortunately, this is not true in the Lambda-adic world. So, unlike the classical case, there is no finite dimensionality is not a good thing to say. But let me just say there's no finiteness result for the number of primitive Lambda-adic forms. tame level n in some character. You can take all the characters together because anyway it's a finite set. No finiteness result for the number of primitive lambda-adic forms. Okay, so this is a bit of a problem. And Hida realized that perhaps the best thing to do is to specialize the definition of lambda-adic form to include only the p-ordinary lambda-adic forms, or actually add another condition, and then try and see what happens. And it turns out that in this case, the number of p-ordinary primitive lambda-adic forms is in fact finite. Okay, and today I'll try and sketch a proof of that, or at least I'll give some motivation of why something like that would be true. And that is maybe the first result in Hida theory, which was the title of the section today. And then I will list some other results, which I probably won't have time to prove, whether or not a form lives in a family, whether the family that it lives in is unique, etc. Some information about those kinds of results. Okay. So anyway, let's get to the finiteness of the number of primitive lambda-adic forms of tame level n in the ordinary case. Before that, let's define ordinary.
Sir,
yes,
sir.
Yes, yes.
Is there any reason why there is no finite result for this, the general case? I mean, is there any two-line reason or something like that, or is it something deeper than that?
Just not true. I don't know how to say that in a short way, but so maybe once I describe this lecture in the ordinary case, you can remember to ask me the question in half an hour or 145 minutes, okay?
Okay.
I'll try and explain why the ordinary cases are finite. And then from there, the ordinary lambda-adic forms are finite. From there, you can try and guess why it just doesn't hold.
Okay.
It turns out, okay, since you're asking for the next 45 minutes of lecture in this question, but let me just give it anyway. And that is that when you specialize, the number of ordinary forms that you get turns out to be constant. Okay, so this is like a rather remarkable thing, that the number of ordinary forms that you get in the spaces of modular forms that we're looking at after specialization, the number of primitive forms whose p-adic valuation is 0 is more or less constant. It's constant. Whereas if you allow arbitrary slopes, if you take the valuation of the p-Theory coefficient to be arbitrary, they're not constant.
Oh,
so there's no way to glue things together. So you have a weight space k is varying. Of course, the dimensions are tending to infinity, right? The space of one
yes.
k in level n. Let's fix zeta to be 1. So let's look at sk gamma 1n, but the key part of the Neyman type stuff is fixed. In that case, anyway, the dimension is tending to infinity. But if you look at the ordinary forms there, the number of zeros, you write down the evaluations of the p-Theory coefficients for a basis. You'll get 0, 0, 0, 0, let's say 5 times. And then you'll get some 1, 1, 1, 1 for the valuations of, let's say, the slopes of form 1. They could also have half, for instance, as a valuation. But I'm just taking some integers and so on and so forth. So the numbers of zeros will remain constant as the weight varies, but the numbers of halves and ones and twos and threes, they'll be quite erratic.
Okay.
So there's no way to glue all those things together.
Okay. Okay, sir.
Yeah. Okay, so say F is P ordinary, a P ordinary lambda-adic form, if, again, whenever you want to define something for a lambda-adic form, the best way to do it is just to say that all the specializations have that property. So nu F, and again, nu lies over, I'll stop writing this, but I mean arithmetic specializations, right? For all k greater than 2, r greater than 1, zeta belonging to mu p r minus 1, I keep writing that. All these specializations are p-adic units. Is a p-adic unit. If for all the quantifier should be up here, is a p-adic unit. Okay, that means Vp of AP of nu of F. How many brackets do I need? 1, 2, 1, 2, 1. One more maybe? I'm not sure. 1, 2, 3, 4, 1, 2, 3, 4. Yeah, equals 0. Okay, so this is a valuation and this is a specialization. One is a V and one is a nu. The p-Theory coefficient has p-adic valuation 0. P does not divide AP. After specialization, P does not divide AP. So nobody has really asked me this yet, and you may be wondering this, and it's probably making you a bit uncomfortable. So it's probably good to say this now. You know, modular forms are usually complex holomorphic functions, right? And the Fourier coefficients are complex numbers. On the other hand, all the things I'm doing, they are for p-adic numbers. Okay, so whenever I do this, I'm assuming that all my specializations are actually taking values in algebraic numbers, q bar. Then there's no issue because q bar sits in the complex numbers and q bar also sits in the p-adic numbers. And so you can transfer properties from one to the other. You can think of it both as complex functions, complex Fourier coefficients, or as p-adic Fourier coefficients, okay? So maybe I should emphasize here that under fixed embeddings, you know, like for example, if you have an integer, a modular form with integer Fourier coefficients, and of course it has complex coefficients and it also has p-adic coefficients. Under fixed embeddings, q bar sitting in complex numbers and also sitting in qp bar. Okay, so we're always fixing such embeddings whenever we're making definitions of p ordinary, because this p-adic valuation is actually a function on qp bar, and then you restrict it to q bar, and then it makes sense to speak about the p-adic valuation of something. Okay, so that is just a comment, but I should have said it a long time ago. Okay, so let us recall now what the space of ordinary, or let us give some notation for the space of ordinary lambda-adic forms. So recall the UP operator, we just said this, acts on the space of lambda-adic forms and the space of lambda-adic cusp forms. It preserves cusp forms, by the way. It acts, so we let E be, this is a bit strange definition, the limit as n tends to infinity of UP to the n factorial. And this is what is called Hida's idempotent. Hida's ordinary idempotent. Okay, so except for a second that this limit exists, I'll try and motivate it in a second, what the limit means. Then you get this operator E, which is the limit of the UP operators. And it has the property that it's an idempotent, E squared is equal to E. So you can make E act on various spaces, and that's indeed will be the definition, formal definition of the space of lambda-adic forms, or ordinary lambda-adic forms. Okay, so then set, this is the definition, M ordinary n lambda to be operator E acting on the space of lambda-adic forms, and S ordinary n lambda to be the operator E acting on the space of lambda-adic forms. Okay. So I'll try and these, for it's not so obvious right now, but these spaces here are exactly going to be the p ordinary lambda-adic forms. Then you project.
What is the topology on these operators? Space of Hicks operators.
Yeah, that's a good question. So right now I'm not speaking of any topology. E will just be an idempotent, something such that E squared is equal to E. But this limit I'll try and motivate using some topologies. Okay, I'll do that in a second. It's a little bit complicated.
Okay.
Yeah. So in fact, what you do is you make E act on finite dimensional spaces of ZP modules, and there you just take the usual p-adic topology if you have a finite module over ZP, and the UP operator acts there, and there you can take the limit, and then you lift the E operator from these finite spaces to the lambda-adic space. Okay, I'll explain it a bit more in a second. But let me just finish the sentence here that I wanted to say. Turns out that these spaces are finitely generated. And in other words, if you throw in the ordinary condition, p ordinary condition, then the number of p ordinary primitive forms is going to be finite. Turns out that these spaces are finitely generated as I modules. And this is the beginning of the first result in Hida theory, that the ordinary forms are basically a finite type. Can I go to the next page?
Yeah.
Okay, so let me try and answer the question about the idempotent and the topology, etc. It's a good question, and it's always a bit confusing, and it is important to understand what it is. All right, so what does this limit mean? Okay, let me not write that, sorry. What is the page number? 19. More on the definition of E. The idempotent E. So let's start very, very slowly. Let's go to the classical world of just not lambda modules, but just O modules, and even not just O modules. Let's look at the very simple setup. Okay, this is a very simple limit that I want to do to motivate you. So suppose you have an X, which is an O, which is the ring of integers of a finite extension of QP. Take a finite extension of QP and take its ring of integers. So my first claim is that the limit as n tends to infinity of x to the n factorial in fact exists and is an idempotent. And in a field, there are very few idempotents. What are the idempotents in a field? Can someone answer me? E squared equals E in a field. Of course, it's an OK. The limit will exist in OK, but it's in K also. So somebody want to answer that before I write what it is? Equals. Suppose E squared is equal to E and you're in a field. What are the possibilities for E?
Only 0 and 1?
Exactly, because you're working in a field, right? So E squared is equal to E means E times E minus 1 is 0, and you're in a field. So E is 0 or E is equal to 1. And indeed, this is what happens. This limit is either 0 or 1. So it turns out to be 0 if X is in the maximal ideal of OK, and it's 1 if X is not in the maximal ideal. It's in the units. Okay, so let's prove this. Indeed, so this is supposed to be just, something from basic stuff in p-adic numbers, not very deep, but I think it would help to talk about this a little bit. So let's look at the following exact sequence, which has come up quite. Let me just write O for OK, so I don't have to, and M maybe for MOK. So let's look at the following exact sequence. Sorry. O mod M to the R, yes, that's correct. O mod M R star, and then let's project to O mod M star, and let's get this exact sequence. Abelian groups, maybe I should write 0, but they're multiplicative groups. I'm not sure whether to write 0 or 1. Okay, so from O mod MR, this is like Z mod P to the N. Z mod P to the N to Z mod P, you have a map. And on the units, you have a map, therefore. And the kernel is just 1 plus P Z mod P to the N. Right? So you have this exact sequence. This shows that the cardinality of O mod M to the R star is Q to the R minus 1 times Q minus 1, where Q is the cardinality of O mod M to the R, O mod M. Okay, so O mod M is a field. M is a maximal ideal there. So this is a field, its cardinality is the power of P, let's call it Q. And this field here is the non-zero elements of a field, so that gives you the Q minus 1, right? And here, and this group here will have the cardinality of this times this. But what is this? Well, it's like P Z mod P to the R. So that one of the P's cancel and you get like a Z over P to the R minus 1. And that was in the simple case, but in general you get a, so that's p to the r minus 1, but in general you get q to the r minus 1. Okay, so we have this more or less obvious formula just from doing a small short exact sequence. Okay, so in particular, if you raise any element to the cardinality of the group, you of course get something trivial. So if you take x and O star, OK star, when I'm writing it as O star, then x to the this cardinality q minus 1 is 1. I mean, it's 1 modulo mod mr. Okay, so this is the first observation I want to make. So now let's let n vary and let r be the largest integer such that this number divides n factorial. If r is largest such that q to the r minus 1 times q minus 1 divides n factorial, let n vary and then r will vary. Then what do we note? X to the n factorial is x to the qr minus 1 q minus 1 times n factorial over q to the r minus 1 q minus 1, right? Because these two cancel. But this is already 1 modulo m to the r. So this is also congruent to 1 because it's a power of something congruent to 1. So it's 1 mod m to the r. So what is this saying? This is saying that as you let n vary now we take limits. As you let n vary, as n gets larger and larger, anyway, x to the n factorial is going to be congruent to 1 modulo a larger and larger power of r, namely the largest power of r, such that q to the r minus 1, q minus 1 divides n factorial. Okay, and of course, as n tends to infinity, r will tend to infinity because you'll have more and more powers of p in there in n factorial. Okay, so the limit exists. Did everyone understand this last thing? Do I have to write it? So note, maybe I'll write one line. As n tends to infinity, r also tends to infinity. So the limit exists. And you can even compute the limit because it's always just 1 modulo m to the r. So the limit is in fact equal to 1. Maximal ideal. Okay, so we just computed the second line, and the first line here, we just checked the second formula here. The first one is obvious, and I won't even write it down. If x, sorry, I wrote exactly the opposite. I did the second one here. That's what I wanted to write here. If x belongs to O star, because I took something in O star, then looked at this image here, modulo m to the r, etc. And the first one here is completely obvious because if x is in the maximal ideal, then of course powers of that will be divisible by, I mean, they'll be in powers of the maximal ideal. So the limit will be in 0. Intersection of all the things in the maximal ideal is just 0. Okay, so we just checked this claim here. Okay, so this limit of doing to the n factorial is not as strange as it looks. It's just a convenient way to hide this whole computation of taking the largest r such that q to the r minus 1 times q minus 1 divides n factorial. Okay, so now this is just if you're in if you're taking the limit in a p-adic field. What if you wanted to take a limit in a O module? So now suppose that A is a finitely generated finite type O module generated over O. I mean, finite type, okay, finite generally commutative O algebra. Okay, can we still make sense of this limit? And then,
can you slide the page up a bit?
Yes, sorry. I'm claiming that this limit still exists. The limit as n tends to infinity, x to the n factorial still exists and is an idempotent. In other words, E squared is equal to E. So now we're not working in a field anymore. So you may have some strange kind of idempotence, right? They don't have to be just 0 and 1. All right, so can I flip the page? Any questions?
Yeah, can flip.
Sure. So why is this true? That in a commutative O algebra of finite type, you still have this limit. So indeed, let's try and prove it for commutative O algebras of finite type as an O module over O. Finite type as an O module. So suppose A is semi-simple. Now, what does that mean? This is more or less by definition. This is the easiest case. It means that when you tensor the O module A by K, you get a product of fields, finite product of field extensions of K. Okay, I won't write notation here. It's just a finite product of field extensions of K. That's what semi-simple algebras, what happens to them after you tensor with K. So what does X map to? If you have X in this X tensor 1 maybe, which is in here, well, it maps to a bunch of elements in these fields, which I'll call Xi. Now, when you take the limit as n tends to infinity, well, what happens? That's the same thing on this side. There's an isomorphism of fields. What happens on this side? On this side, you get individual limits of each of these things. Over I. There's a finite. Okay, and we just said that each of these is 0 or 1, right? Because we're working in the field, which is a finite extension of K, which is a finite extension of QP. Okay, and this shows, therefore, that E is an idempotent, because it's basically an element of, it's got these many entries as the number of fields that there are, and each entry is 0 or 1. And so the square of that element, well, is also exactly the same element. 0 times 0 is 0, 1 times 1 is 1. So when you square such a tuple, you will get another idempotent. Okay, so this should be enough for now, but I will also maybe mention briefly what happens when A is not semi-simple. If A is general and finite type over O, then you write X as S plus N, where S is semi-simple element and N is a nilpotent element. Okay, nilpotent means at N to the J, there exists a J greater than or equal to 0, such that N to the J is equal to 0. And now, if you look at S plus N, by the way, this is bad notation in the sense that N was also the N appearing in this limit, but I don't know. Yeah, I hope you're not confused about that. This N here is just now a new N. It's a nilpotent part of X. If you take S plus N to the Q to the R, well, by the binomial theorem, it's S to the Q to the R plus the sum I equals 1, not 0, because I pulled out the S to the Q to the R, J minus 1, because N to the J anyway is 0, so many of the things will become 0 here. Q to the R, choose I, S, Q to the R minus I, N to the I. Right, just the binomial expansion, but I'm terminating this at N to the J. I'm not taking things beyond N to the J. My I is only stopping at J minus 1, because N to the J is 0 and all higher ones are 0. Okay, now we use a very beautiful fact from classical number theory. What are the p-adic valuations of binomial coefficients? So there's a lot to be said about this. The p-adic valuation of n choose m is basically the number of carries that are required in base p arithmetic when you add n minus m and m. So n minus m is some number and m is some number. They both have base p expansions. When you add those numbers up, your digits have to be between 0 and p minus 1. So you may have some carries. And the number of carries you get is exactly the p-adic valuation of n choose m. So using that formula, classical formula, I think it's Kummer's theorem from a long time ago, we know that the valuation of q to the r choose I is fr minus the valuation of I, the p-adic valuation. But, okay, but j is bounded. The j was fixed. J only depends on x. And therefore, I is also bounded. I mean, j is fixed and I is therefore bounded. So this p-adic valuation is bounded. But now if you let r tend to infinity, then this p-adic valuation is getting larger and larger, right? So this whole term u to the r minus I n to the I n choose I is in fact going to 0 in the p-adic topology.
Excuse me, what is F here actually? Maybe I missed it.
Sorry, yeah. F is just always the, no, I didn't define it. Thank you for asking. Q is p to the f. Yeah, infinite field theory, that f. So Q is a power of prime, so it's p to the f. So maybe you're more familiar with this theorem when you write p to the r, choose I. And then it's r minus the valuation of I, but this Q really has a p to the f in it. So it's p to the fr. That's why you get an fr here. Okay, so this latter part here goes off to 0 because the valuations of the binomial coefficients are going to 0. And therefore the limit as n tends to infinity, same notation, but different n now. Maybe I won't write n here because it looks confusing. Q to the r tends to infinity, s plus n, q to the r exists. I don't know what to do. Okay, let me write n only. But the r is the largest r, such that q to the r minus 1 divides n. This limit as n tends to infinity, x to the n factorial, which is this limit, is equal to the limit as n tends to infinity of s to the q to the r, which this exists, right? Because we just did the semi-simple case up there. Like a semi-simple exists in OS, which is inside A. This is a semi-simple subalgebra. Okay, so sorry for the slight abuse of notation, but I think it should not cause any problems. N is both an nilpotent element and a limit. Okay. So that's how you do the general case. Okay. So finally, but these are all O algebras of finite type. So what about Lambda-adic things? So for this, one has to do a small argument, which I won't do in complete detail here. So for an I module A, so I is not ZP or O anymore, right? It's not a ring of integers of a number, p-adic number field. It's like a power series ring. So for this, one defines E in a slightly ad hoc way. So, and you have to do some checks. We define E by gluing, can you see? Maybe I'll move up. By gluing together the EK under the specialization map M n lambda. Remember, if you specialize up to weight k, any weight j, let me write specialized in weight j, mj np, I'm taking zeta to be 1, psi omega minus j, right? I'm taking chi zeta to be 1, I didn't write any zeta, O, where O is a sufficiently large extension which contains the values of the specializations under I. Right? There are only finitely many specializations here between 2 and k. And so they all take values in various p-adic integer rings. And let me take O to be so large that it contains all those p-adic integer rings. So here we have power series rings, and here we have p-adic rings. And these are the specialization map of the Lambda-adic forms. So here we have idempotence by what we said above, right? For each k, you look at the sum from j equals 2 to k of all these spaces of modular forms, and you have this idempotent ek, because this is a commutative O algebra. Okay, I should actually not write M here. I should write the Hecke algebra here. So let me write this as, this is true, but I need one more line, and since I'm running out of space, let me write Hecke algebras here, H. Hecke algebras are the algebra, because these are not algebras, these are just O modules, right? There's no multiplication, but the Hecke operators act on these spaces, and then you can define the Hecke algebra to be the algebra spanned by those operators, and then you have this, this map. So the Hecke operator here induces Hecke operators here, and in particular, you have the idempotent Ek here, which is the limit of the UP operator for each of these. Okay, so the part that I'm going to cheat a little bit about is that these EKs are compatible over here, and they give idempotence. There's an obvious commutative diagram here, where you take K and K prime, and then you have Ek and Ek prime, and that diagram commutes. And so you get a compatible family of these idempotents, and you lift that to the Hecke algebra here. Okay, so that's what I mean by gluing together the Ek under this specialization map. Okay, there's some checks that one has to do there, but maybe I will skip them. Is it reasonably clear?
Yeah, I think it is.
I fudged the last step, but apart from that, up to this step, is it clear?
Yeah, till that it is clear, sir. But
Yes.
what is Ek? Can you Ek
Yeah.
be defined
So-
E? But
Yeah, so they have the space of Lambda-adic forms. These are Hecke algebras, but I had an M before. And they specialize to classical forms from weight 2, weight 3, weight 4, up to weight K.
okay.
K is now the upper index here. And then I have a space of classical modular forms. I add them all up. There's no overlap between these forms. There are different weights and things like that. And for each one individually, I have a idempotent E, right? Which is the limit of the UP to the n factorial. And then therefore I can take the idempotent on the direct sum by taking the individual idempotents at each component.
Okay.
So that's my idempotent Ek. So on this side, there's no issue about defining the idempotent. I just did it. So A, you apply the previous discussion to A to be the direct sum of these algebras.
So Ek is nothing but direct sum of all idempotents in the right hand side.
Exactly,
Okay.
exactly,
Okay.
exactly. Yeah. And now what I'm saying is that Ek idempotent is actually, as you vary K, you get another Ek prime, etc. But those are all compatible under these maps, the Hecke algebra maps. And they live together to give an idempotent on the Hecke algebra Hn lambda. And that is Hida's idempotent on lambda-adic forms. Okay, so that requires a little bit more discussion, which I am skipping. So whenever you see idempotents acting on O modules, you should be completely comfortable because of this discussion above. And whenever you see idempotents acting on lambda modules or I modules, then you need to use this gluing together phenomena to lift idempotents. Okay, so I will move on. 21. Okay, so that concludes my discussion of the idempotent. I thought I'd say a few more words than just writing the limit of UP to the n factorial. That looks a bit more looks mysterious. In any case, we have the following theorem that M ORed n lambda is finitely generated as, let's remember, was E times M n lambda, no idempotent of I. It's finally generated as an I module. Okay, so let me try and sketch now a proof of this. We more or less understood what the idempotent was acting on M n lambda. And I would now like to sketch why suddenly, by cutting out the space of lambda-adic forms and looking at only the ordinary forms, because this is the only ordinary forms, why you will get something which is finally generated as an I module. Okay, so let us talk about this part. Okay, so proof. By the way, I should have maybe said that where did I? You may wonder why, when you apply E to a form, why it's an ordinary form. Because I've given two different definitions of E. But maybe you can think about that a little bit, because, for example, if you have an eigenvector of E, and suppose F is, suppose UP is equal to, UP of F is lambda times F, right? Then that lambda will either be a unit or become zero. When you take, I mean, if lambda is not a unit, then the E will actually kill that particular eigenvector. It'll only make the eigenform survive for which the eigenvalue is a unit. Okay, that's a small computation. Maybe I leave that to you, or we can come back to it later. I should have said that earlier. So these are the space of lambda-adic forms, namely the eigenvalues of the UP operator are units here. Okay, so proof. Why is this finally generated as an I module? So let's assume this proof is really a sketch of a proof, because it uses many things in many books. But I think it's extremely important to do this sketch because it motivates the definition of the finite generation quite well. So assume I equals lambda for simplicity. Okay. So I'm claiming that two facts hold. One, that if you look at the space of ordinary forms, I'm writing gamma 1 NP, so to not write the Nevin typus, ZP, then this is finitely generated of bounded rank over ZP. Bounded means independent of K. Okay, so this is what I was alluding to maybe half an hour ago when I was saying that if you take it the ordinary forms in the space of classical forms, the number of zeros that you get, the number of valuations of the UP eigenvalues that you get, which are zero, so the number of slopes that are zero is independent of K. I mean, it may fluctuate a bit, but it actually turns out to not even fluctuate a bit. There are exactly 10 zeros, let's say. Even though this dimension is tending to infinity, the number of zeros, the valuations of all the eigenvalues of the UP operator, you'll get 10 zeros and then maybe some ones and twos and threes and fours and maybe some fractional values also. But the number of zeros will be bounded independent of K. In fact, it turns out it's actually a fact that it's actually constant independent of K. That's one thing. And once this is true, then maybe it's more believable that the second thing is true. Since M ord and lambda, the space of ordinary lambda-adic forms, under the specialization map, maps to the space in part one, right? I'm writing gamma 1 here, so I don't have to write the Nevin typuses. But if you write gamma not here, then you have to write psi omega minus K chi zeta and things like that. But here I'm just specializing with zeta equals 1. New K1. Since you have the specialization map, you now bootstrap, because these are independent of K, one can bootstrap to show that this is a finite type as a lambda module. One concludes that M ord n lambda is finitely generated as a lambda module. Okay, so this part maybe is not so surprising and I will not do it. What's more surprising is part one, and then using part one to conclude part two. Okay, so we sketch a proof of one. Okay, so now you're going to have to just bear with me for about 5 to 7 minutes because I'm going to use slightly advanced things. But everything here I say is very well understood, and there's no mystery really behind it. And there are things from books from the, from a long time ago, like the Shimmer isomorphism. I'm about to use it now. It's already in Shimmer's book, in his 1971 book, and things like that. I'm going to use a bit of cohomology. So if you haven't seen cohomology before, it may look a bit strange to you, this proof, but I hope it will be some motivation to study cohomology. It's a beautiful proof using cohomology. And by the way, many results in the theory of modular forms become trivial if you use cohomology instead. I'll give you one example, which is easier than this one in a second, maybe, if I remember as I'm writing. So let gamma be gamma 1 NP, so I don't have to keep writing it. And then we have the Shimmer isomorphism, which is in Shimmer's book, for instance. So in fancy language, it's basically decomposing the de Rham cohomology of the modular curve into the holomorphic and anti-holomorphic differentials. But we don't want to use that fancy language here. Let me just write down an explicit isomorphism, namely the space of modular forms of weight k and level gamma is isomorphic to a cohomology group n is k minus 2 now, yet another meaning for n. Okay, so this could be, it starts from 0, 0, 1, 2, because, k was starting from 2 onwards, so n is starting from 0. And LNR is going to be the is equal to going to be the homogeneous polynomials in 2 variables of degree n with action of gamma and this is group cohomology, gamma dot p of xy. So how does group cohomology work? You have a group and then you have a gamma module, right? So once you have a group and a gamma module and a abelian group which has an action of gamma, then you can speak of its cohomology group, say 0, h1, h2. And so I have to tell you what the gamma action is. So if you have a polynomial in 2 variables, p of xy, it's p of, you take the main involution, gamma I xy.
Can you please read that, please? Yeah.
Yeah, sorry. So the way gamma is acting on a polynomial is, it just acts on variables, but I do a slight twist here. So ABCD goes to D minus B minus CA. That's this involution here. You flip the A and the D and you multiply the B and C by minus signs. And then you make it act on the 2 variables, substitute in the polynomial, you get a new polynomial. And that's the action of gamma on the space of polynomials. And then if you look at this group cohomology, the claim is it's isomorphic to the space of modular forms. This is a complex vector space, but the real dimension is twice this, and this is a real vector space, and you have this. And the map is given something like this. So it's group cohomology, so you have to give a cocycle, that means a function from gamma to LNR. What function do you take given an f? Well, it's just the integration function. So you take a point z in the upper half plane, then gamma goes to the line integral from z to gamma z of the real part of the following differential form, f of z polynomial x minus zy to the n dz. So this cocycle, given a group element, you get a real number by doing this line integral. Sorry, you get a polynomial because you get a sequence of real numbers. This, once you expand out x minus zy as a polynomial, you do the line integral on each coefficient separately. And once you're done with the integration, you actually get a genuine polynomial. So each group element goes to a polynomial, and that's the cocycle that you get here, function. Okay, so this is the space of modular forms, and this is group cohomology, and they're isomorphic. And if you look in books, it's a little bit the variants of this isomorphism, but I think this is the one that we want to use over here. By the way, some people ask, why are Hecke eigenvalues algebraic integers? You may have seen this. All of you who have studied modular forms, why are the Hecke eigenvalues algebraic integers? And so I remember to make this comment before going on with this proof. Why are they algebraic integers? Well, they're algebraic integers because the Hecke operators as matrices have entries in Z, right? So if you try and take the characteristic polynomial of a matrix whose entries are in Z, then of course the roots will be algebraic integers by definition almost. But then you can say, but why should the Hecke operators have as matrices? They're just operators, complex operators. Why should you have the entries in Z? Well, some people would do what was asked to me 2 days ago. You have an explicit basis, E4 to the A, E6 to the B, etc., right? And they all have Z entries. So when you look at the Hecke operator action on the explicit Z basis, you get a Z linear combination of the basis elements. So you get an operator in Z, but that's a level 1 proof. What do you do if the level is arbitrary? Then it's very hard to write down a Z basis. So then it's not at all clear why the Hecke operators are matrices with entries in Z. But using the Icloud-Shimmer isomorphism, this fact becomes completely trivial because this isomorphism is actually Hecke equivariant. So it turns out that there's a Hecke operator action on both sides, and the operators, if you do Hecke first and then map over, it's the same as mapping over and then doing the Hecke operator on this side. The Hecke equivariant operator for each of the Hecke operators. So in other words, the behavior on the Hecke operators on the left is very similar, identical to the Hecke operators on the right. So now you're reduced to another problem. Why do the Hecke operators over here have entries with matrices in Z? Well, now there's a very simple reason. And the reason is that the space of polynomials, Ln(R), has a Z structure. You can look at Ln(Z), the space of polynomials with Z coefficients. So if you look at the group cohomology H1 gamma Ln(Z), or more formally the image of that in the real vector space, because there may be some torsion, so it dies, then that lattice is inside the real vector space is preserved by the Hecke operators, and it's a Z structure. So by definition, then all the Hecke operators have integer matrix entries, and therefore you've proved this in one line using the Icloud-Shimmer isomorphism. So this is the power of the Icloud-Shimmer isomorphism. And therefore, all the Hecke eigenvalues are algebraic integers. So even those of you who are not interested in lambda-adic forms, please try and study the Icloud-Shimmer isomorphism. It tells you many things about classical modular forms very quickly. Much faster than trying to come up with explicit proofs purely on the modular form side. Okay, that comment was a little long. Let me move on with this proof. Can I flip the page?
Yeah.
Okay. So, as I was saying, we have the Icloud-Shimmer isomorphism. And so just coming back here, let's just recall what we were trying to do. So I was trying to show that the space of ordinary forms, if the Taine level was fixed, but K was varying, then the space of ordinary modular forms was bounded independent of K in dimension or in O rank. And what we're doing is we're going to transfer that to a cohomology computation because of the Icloud-Shimmer isomorphism. So you can believe after what I've just said that it's Hecke equivariant. To show one, it's enough to show that the ordinary part of H1 gamma Ln(ZP) is of bounded rank independent of n. Independent of n, yeah, okay, K is n is K minus 2, so it doesn't matter which one. Rank independent of n equals K minus 2. Is the ordinary part of the cohomology. Okay? So H1 gamma Ln(Z) was sitting in H1 gamma Ln(R), and the image of that is a lattice. And so we want to show that is bounded, but this is a p-adic computation. So you can look at E acting on H1 gamma Ln(Z) P, and we need to show that this is bounded. Okay? So I maybe skipping one or two smaller steps in between, but I'm giving the broad lines of the proof. So I hope this is motivated now, that we need to show some cohomology group has bounded dimension, at least the ordinary part of it, as n tends to infinity. So how do we do that? Well, here's a very beautiful computation, and this is at the heart of Hida theory. We look at the short exact sequence of gamma modules. This is multiplication by p. You take a polynomial and multiply by p. So it's a small p now, not capital P. And then you get z mod p, zp mod p zp, which is the same as z mod p. So we have the following short exact sequence of gamma modules. Let me write things because it's not so clear when you don't write things. Consider the short exact sequence of gamma modules. This gives, in my cohomology theory, and this is the whole point of cohomology, gives the long exact sequence of cohomology groups H1 gamma ln ZP, H1 gamma ln ZP, H1 gamma ln Z mod P, and so on and so forth. There's H0, H0, H0 here, H2, H2, H2 here. It goes on in both directions. Okay? This is the multiplication by P map. On the polynomials, it's multiplication by P. So on cocycles, it's also multiplication by P. So now if you take the ordinary part, I'll put a little e here, you get this. Okay, so therefore, and e, so therefore, we get e of H1 gamma ln ZP modulo P times E gamma ln ZP sits in E of H1 gamma ln ZP, Z mod P. Okay, so I just use the first isomorphism theorem here. The kernel of this map here is the image of this map. That's what it means to be exact. The image of this map here is P times the cohomology group. So domain modulo kernel is isomorphic to the image, but the image is sitting in the target. So there's an inclusion like this. Okay, E of H1 ln Z mod P. Any questions so far? Is it okay?
Yeah.
Okay, good. So, therefore, it is enough to show, remember, we wanted to show that the numerator here, oh, I wrote an E here? Yeah, E, enough to show. Right? The numerator here was of bounded rank independent of n. But what I did is I went mod P, you know, if you have a ZP module, ZP plus ZP plus ZP, rank 3, if you go mod P, you get Z mod P plus Z mod P plus Z mod P, right? So whether you show it's a ZP module of finite rank or whether you show mod P, it's a finite as a Z mod P module, vector space over FP, it doesn't really matter. So by this, to show that this is finite, which is a Z mod P module, there's also a Z mod P module because of this, it's enough to show that the ordinary part of H1 gamma ln Z mod P is finite, is a finite dimension, is a bounded dimension as n tends to infinity. Okay, so that cohomology allows you to do that reduction. I'm going to do one more reduction. So let I, not iota, be the map which takes a polynomial to its x to the n coefficient. Okay, so if you have a polynomial xy, let's take it to the coefficient of x to the n. Okay, so again, you get a short exact sequence. 0 goes to kernel I, goes to ln Z mod P, goes to Z mod P, goes to 0, right? This is the map I. You're just taking a polynomial and taking it to the coefficient of x to the n. So, you know, this is x to the n plus something times x to the n plus something times xn minus 1 y plus something times xn minus 2 y squared all the way up to something plus something times y to the n. I just take the coefficient of the leading. Okay, so this induces another short exact sequence here, induces another long exact sequence on cohomology, which is, and I won't write the H0 terms, H1 gamma kernel I, H1 gamma ln z mod p, H1 gamma z mod p, and then it wraps around to H2, H2, H2. So you get H2 gamma kernel I. And then H2 gamma ln z mod p H2. I just need this part. Okay. So remember, we were trying to show that this had bounded dimension. If I can show that this group and this group become 0 after you apply the idempotent, E kills this and E kills this, then this will become an isomorphism, and we will get the conclusion exactly what we wanted. E times H1 of this is E times H1 of this, but there's no N here. N has gone away. It's like N is equal to 0. But N equals 0 is weight 2. So what we're going to conclude is that the space of ordinary forms of any weight is the number of ordinary forms, ordinary primitive forms of any weight is exactly going to be the number of ordinary forms of weight 2. And that's why it's a bounded dimension. Okay, so let's carry out those steps. So recall the TP operator, which I said is called UP, is the following Heck operator. It's gamma 1 NP, 1P, it's a double coset operator, right? Which is a disjoint union. I remember I said there were P representatives. Gamma 1 as a double coset, if you decompose as single cosets, it's 1U0P, okay, which I'll call, let's say.
Can you please slide up, maybe?
Yeah, sorry, which I'll call alpha U. By the way, I'm not talking about my own research or anything here. I'm talking about things from 30 years ago. So if you're feeling I'm talking about my research or something, it's definitely not like that. This is this computation I'm doing is from Hida's undergraduate textbook on modular forms. But I think that is perhaps a little ambitious to have that kind of title, elementary theory, and it's an undergraduate textbook. But I want to emphasize that he considers it at that level. So, and these are very old things. So maybe you will be motivated to look at it. Okay, so the Heck operator UP is this, and now we want to take the limit of UP to the n factorial and make it act on these various things, and we want to show that E kills this, and these are become isomorphic. So let's do that computation. So how does it act? It acts on a cocycle C from gamma to ln z mod p via C of gamma. Can you see here? I hope you can see. Gamma is in gamma, little gamma is in capital gamma, is the sum over U equals 0 to P minus 1. Alpha U matrix, this is the coset representatives. You take the main involution, you flip the A and the D, and you put minus B minus C. Acting on the polynomial C of gamma U prime, where, so given a gamma in here, and an alpha U is also in this double coset, this element, alpha U gamma, is not in this. I mean, it's in here, but it doesn't respect this right coset decomposition. Sorry, this left coset decomposition. Oh, I always forget. Is this the right coset or left coset for those of you who have just done first year algebra? I think these are right cosets, right? The representatives on the right. So what I've done here is I put the alpha U on the other side of gamma. Okay, so it's on the wrong side here. Gamma is here, alpha U is here, but I flipped it. So you can, because it's an element in the double coset space, you can write it as a gamma U prime times some other alpha U prime, right? There exists. And there exists U prime, such that alpha U for each U, alpha U times gamma is gamma U prime times alpha U prime. So that how canonically given a gamma, you come up with a sequence of gamma U primes, and you put the gamma U primes, you collect all the gamma U primes together, evaluate the cocycle on the C of gamma U primes, you get some polynomial. You make these alpha U's act on the polynomials, and you take the sum of those polynomials, and you get C of gamma. So this is how the Heck action is defined. So for the first time, I actually had to do something explicit here. I couldn't get away with just saying there's a Heck action on homology. But this is the Heck action on homology. So now you've seen it. Okay, I'll flip the page, and I won't pause because it's not that much time. 23. Well, let's look at alpha U acting on iota acting on a polynomial. Let's do an explicit computation. Well, it's 1u0p acting on p of xy, right? I write it as a column vector because the action is as column vectors, which is p of 1u0p acting on xy, which is p of x plus uy, right? py. So this is a small computation. Now, what does this say? This says that if C is a cocycle which takes values in the kernel of I, in other words, kernel of I means it's all the kernel means it's spanned by the polynomials which are just in the span of the x to the n minus I, y to the I for I greater than 0, right? So they're the ones with y in them, or they have a power of y in them. Those are in the kernel of I, because I was the map which took the x coefficient. So if you have a cocycle which takes values in these special kinds of polynomials with no x coefficient, and you make Heck operator act on it, then what's going to happen? When you look at the formula, which was on the previous page, unfortunately, I'll put it right here. Alpha ui c of something, and suppose that this now c is taking values not in ln zp but in the kernel, so in this cohomology group. And what's going to happen, because there are always a power of y, you get a p pulling out. Okay, so the up operator always multiplies by p. Well, that means that when you apply the ordinary idempotent to any cohomology group, this is just for one cocycle, but I could take I copies of, yeah, it's the same argument, but okay, let's do for one. H1 gamma ln z mod p is actually equal to 0. Right, because the up operator multiplied, sorry, this is completely wrong. This is on the kernel of I. For special cocycles which are taking values on the kernel of I, the up operator multiplies such cocycles by p, and so when you take the limit of up to the n factorial, you'll get higher powers of p, and it'll just kill everything, right? Things which are divisible by high powers of p in this world where dictator decrees in the p-adic topology, two things are close. If they're highly divisible by 125 or 625, etc., like, right? Those things just die. So you have this. Sorry, I don't know why I marked my notes. H1 gamma kernel I is equal to 0, and exactly the same computation, which I was trying to do at the same time, but I noticed I only took functions on gamma, but you have to take functions on gamma cross gamma and define the action. Exactly the same argument shows that the ordinary idempotent kills the other cohomology group at the other extreme, H2 of gamma kernel of I. This one. So moral is that H1 gamma ln zp z mod p for arbitrary n is isomorphic to H1 gamma z mod p, at least if you take the ordinary parts. Oops, can you see that?
Yeah, now we can see.
Yeah. I just killed the two extremes here, and after applying the ordinary idempotent, it killed these two things. So those things in the middle became isomorphic. This is bounded independent of n. Okay, so this is a sketch of the proof of the theorem. And the moral of this is, if you didn't understand anything, is that the number of Lambda-adic forms is unbounded, but if you put the p ordinary condition in, the number of p ordinary Lambda-adic forms is equal to the number of weight 2 p ordinary forms. Right, because weight 2 is k is 2, so n is 0. Here n is 0. It's the polynomials with n equals 0. Okay, so this is the computation which shows that when you put the p ordinary condition in, there are not too many Lambda-adic forms. They're just depending on the weight 2 forms. So I'll pause for a second, and now I can state the main theorem of Hida theory, which I will not prove. I've already proved the first part more or less. I sketched it. Any quick questions?
Maybe later on you can say a little bit why E operator gives you that ordinary forms, like that p-adic valuation is 0. I think you said a bit.
Yeah, I'll come back to that in there. Maybe I'll just state the main theorem. Otherwise, I haven't stated the main theorem yet. So here's the main theorem of Hida theory. So assume P is bigger than 2. Some of Ganesh's students are watching, so let me mention that the P equals 2 case was done. So this is in 2 papers of Hida in 1986, Hida 86A and Hida 86B. This is in Inventionist Math. This is in Alzines, the Journal of the Alzines, Journal of the ENS. So these are 2 papers, but for P equals 2, C work with Narasimha Kumar, and I don't remember the date, maybe about 10 years ago we did something, and it's in one of the TIFR conference proceedings, where some of these issues were cleaned up for P equals 2. So what is the theorem anyway? So there exist finitely many P ordinary, I just said this already, P ordinary primitive Lambda-adic cusp forms. Let's work with cusp forms in this theorem. So you can drop the word cusp here, F of tame level N and some character psi. Second, now this is the part that I haven't proved in this lecture or even sketched the proof, but they're very clean statements. Every classical form lives in a family. Every classical P ordinary, P stabilized, primitive cusp form of tame level N. Sometimes you write N or NP, it doesn't matter, tame level N. Weight greater than equal to 2, K greater than equal to 2. And Neven typus chi, this is a decomposition of an arbitrary character into its tame and wild parts. Chi zeta lives in some family, primitive Lambda-adic form. Of character psi. Okay, it's a specialization. So every classical form lives in some family, in some Lambda-adic form. Okay, so this is the second thing. And the third thing I want to say is that the family in 2 is unique. Okay, so every weight 2 or more form, classical P ordinary form, lives in a unique family up to some Galois conjugacy, but I won't get into that here. And the last thing I want to say, and this is what going to be the content, these 2, well, okay, let me say the last thing. Given F as above, there exists a Galois representation, rho F, from the Galois group of Q bar over Q to GL2 of KF. KF is a finite extension quotient field of lambda, which I call K. This Galois representation has many natural properties, which I'm going to now. Okay, there's a Galois representation. It interpolates, for example, all the classical Galois representations, which we mentioned at the beginning of lecture 1. So all those Galois representations are going to be interpolated by a huge Lambda-adic Galois representation. So Hida constructed these Galois representations, and we actually talked a little bit about them in the discussion section, which somehow allowed me to introduce them, but I will introduce them much more formally in the last lecture. So where are these proofs coming from? I've run out of time. Even though I started 5 minutes late, I'll stop on time. So let me just say one thing, and that is that this one we already sketched a proof of. There are finally many lambda-adic forms. The second one, that every form lives in a family, is coming from the fact that the specialization map is surjective. Okay. Another way to say that is that the map of Hecke algebras under specialization is also surjective. You can recover Hecke eigensystems, classical Hecke eigensystems from lambda-adic form, like lambda-adic Hecke eigensystems. So this is that statement. And they're under the notion, they come under what are called control theorems. Like when you specialize the lambda-adic Hecke algebra at some height 1 prime corresponding to nu, when nu is a arithmetic point, then you actually get a classical Hecke algebra on the nose. It's an isomorphism. Now, those are called control theorems, and this is what we also do with Narasimha Kumar for p equals 2. Hida proved these things for p odd. Sorry, I said I wouldn't say anything about my research, but they're just a little addendum to the literature. The final statement 3, that the family in 2 is unique, is also coming from classical Hida theory, and it is a statement about the etalness of the Hecke algebra over lambda at arithmetic height 1 prime. Okay, so Hida proves such etalness statements, and then it follows that the family is unique. So these are sort of casual ways to say certain things, but they have some more formal interpretations in terms of Hecke algebras, control theorems, etalness statements, and they imply these properties. The construction of the Galois representation I'll do next time in a lot of detail, actually. So I'll prove one I've kind of sketched, and 4 I will prove in some detail. And 2 and 3 I will not do in this course. Okay, so I will stop here.